In March of 2020, face-to-face lectures were abruptly cancelled due to the COVID-19 pandemic. In our case, it was almost time for the recess, so students went on holiday. However, as lecturers, we knew that we would soon be starting online teaching, and we had to figure out the best way of doing that. In my case, I decided to use videos. We would be teaching for a couple of weeks or a couple of months, we didn't really know, but now it's been basically just over a year that we've been teaching online. And I am now in the fortunate position that I can begin to reuse some of the videos that I produced hastily back in April of 2020. Fortunately, not much has changed in the subject, so the content still is mostly true, and I will only have to make changes where changes should be made. However, it gives you, the viewer, also a nice opportunity to observe what has changed and what hasn't changed, and perhaps tell me what works and what doesn't work. It is time to continue our discussion of computer networks. Previously, we looked at various applications that fit into the application layer of a computer network. In this video, we're going to move down one level in the protocol stack to layer 6, the presentation layer. And as the name indicates, the presentation layer deals with the representation of information. Stated slightly differently, the question is, how does one encode information on one end of the network such that it can be decoded in a meaningful way on the other side? If you think about network applications, you probably immediately have many examples that come to mind. Videos that are streamed across the network. Perhaps you are viewing images across the network. Or you're listening to music or other sounds that are streamed via the network. And the presentation layer has to deal with all these different types of data. However, in today's lecture, which is the first of 4 lectures that will deal with the presentation layer, we are going to look at what seems like a very simple example. Characters. In other words, letters like A's and B's and C's. Now, that does indeed seem like a trivial example, but it is not quite as easy as it seems. One way to illustrate that, a book that was written in 1980 with the title Coded Character Sets discusses a lot of issues that one has to consider when you transmit data across the network. And as is obvious, it's a pretty thick book. So there's a lot to discuss. Fortunately, we won't have time to discuss everything, but hopefully we'll be able to discuss enough of it so that you can get some sort of a feeling of how to transmit one of the simplest possible data types, characters. In the early days of computing, the designers of those computers somehow had to decide on a mechanism to represent data in the computer's memory. This happened in around the 1940s for mainframe computers, and the same process repeated itself in the 1970s for microcomputers. In principle, the problem is rather easy to solve. If I, for example, have a couple of characters that I want to represent, an A and a B and a C, then one option is to say that I'm going to represent that character A with a value 1, and that character, the B, with a value 2, and that character C with a value 3. Obviously, all modern computers are digital, So these values will somehow be converted to a digital format. The 1 will be a 1, and this leaves us now with a question: how many bits do we want to use to represent that character? And to start off with, let's say we use 4 bits. It means the B will become, or will be represented using that bit pattern, and the C will be represented using that bit pattern. Now, this leaves us with a couple of questions. One of the questions is, when I see a specific value, for example, when I see that value, how do I know that it represents a B and not the binary value 2? And the answer is straightforward. It depends on what we expect to see there. So if I get something via the network for a given protocol, I typically know what to expect. Think of the SMTP protocol. Recall that the very first instruction in the SMTP protocol was one where you said hello, or the extended version extended hello. So what you expect for that protocol are those characters. And if you see the binary numbers that arrive and they agree with the representation of those letters, then you know that you've received the correct text message. Another question that we have to ask is whether our 4-bit encoding is sufficient. Now, with 4 bits, you know that you can represent 16 possible values. How many do you want to represent? Well, you want to represent the entire Latin alphabet, that's 26. You probably want to represent lowercase and uppercase, which means there may be another 26. You probably want to represent all 10 the digits, and then you need to represent some punctuation, full stops, commas, and so on. Conservative guess, let's make that about 10, which means at the very least you want to be able to represent 72 different characters. Probably more, but 72 may do it. Our 4-bit code only allows us to represent 16. A 5-bit code will do 32. It's not good enough. A 6-bit code will allow us to represent 64. Our choice that we made is not met by a 6-bit code. But if we are willing to forego lowercase characters, then a 6-bit code may well work. And some 6-bit codes have been used in the past, and then you only had uppercase characters, and it did work indeed. But what we need, if we do want lowercase, is at least a 7-bit code. That allows us 128 characters, which means we can cover the essentials and we can cover a bit more. The problem with the code that we've just designed is that it is our design, and we can only talk to other computers if they use the exact same code. And people are not automatically going to use the exact same code, and therefore we need some form of standardization. The first example of a code that formed a type of de facto standard was the extended binary coded decimal interchange code, EBCDIC. EBCDIC is not a standard. It was developed by IBM. It's proprietary. It was developed in the early 1960s. But one of the things to keep in mind is that IBM was an extremely prolific player in the field of networks at that time. It was the dominant provider in the network market. And chances are that if you build a network, you communicated or would have communicated with an IBM computer, and you may even have used IBM equipment, even if you were not an IBM user primarily. So chances were pretty good that you would have had to convert whatever code you were using, if it wasn't EBCDIC, that you would have to convert that to EBCDIC and convert back from EBCDIC. That's not an ideal solution, because EBCDIC is an 8-bit code. In principle, that means it allows 256 characters to be encoded. If you use a 6-bit code, then you have many fewer characters. And in principle, it's possible to convert your characters to EBCDIC, but you may get responses that you cannot convert back to your code. And even if you are using a 6-bit code, it is possible that you may have characters represented that are not represented in EBCDIC. So it is not an ideal situation where one has to convert to some de facto standard. We also need to say a couple of things about EBCDIC based on the era from which it comes. The basic, most prominent form of input in the 1960s was punched cards. And if you look carefully at a punched card, you will see that the rows on this punched card have zeros through to 9. In other words, this is a decimal input device. If you want to represent the value 123, then you can punch the 1 in one column, a 2 in the next column, and a 3 in the following column. Exactly where it will be spaced on the card is something that depends on the program. We don't have to consider that. But in essence then, we have decimal values that need to be represented, and that's why we have the BCD part, the binary coded decimal part, in the name of that code. But we don't only want to represent numbers. We want to represent characters. And that's why it's necessary to extend it. The way in which it was extended was to add so-called zone rows. And what you can see on this particular example is that there are rows of holes at the top, above the numbers. In fact, there are 2 rows of holes here, and the row with the zeros is also considered a zone row. So the way in which an A is represented on this punched card is that the topmost row will be punched, and a 1 in that same column will be punched. A B will also use the top zone row plus a 2, and so on. And once you get to the end of that, in other words, after 9 characters, you can represent the next 9 characters by punching a hole in the second zone row, and then combine with that digit from 1 to 9. The third set of characters, you can in principle do the same thing, except this time you will punch the 0 and the corresponding number. And that gives you in principle 9 plus 9 plus 9 is 27 different characters, in addition to the digits that you can punch by just punching out the corresponding digit. However, there was a quirk in these early punch card machines that caused the readers to fail if you punched 2 adjacent holes in a column. So in our last example, where we spoke about punching a 0 and a 1, that was potentially a problem. And therefore, the 0 and the 1 were not used as a combination. And the first character in the third zone was therefore the 0 and the 2. So in the last zone, you only had 8 characters, not the 9 you had in the other cases. So that provided you with 9 plus 9 plus 8, 26 characters. That is enough to represent the alphabet. ASCII was extended beyond this. There was another zone row included. But even to this day, we are left with a code, ASCII, where there is a space, where there is an illegal character combination in the character codes due to a very old technology that used to jam. It's also important to note that ASCII in its name already indicated that it was intended to be used for interchange purposes, to send data from one machine to another machine. The first real code that was designed for interoperability was ASCII, the American Standard Code for Information Interchange. ASCII, first of all, is an American code, an American standard. So it makes sense that ASCII would represent something like a dollar sign. In America, they need that. However, ASCII does not make provision for representation of a pound sign, because in the United States they don't need that. The way in which this problem was solved, because they did want ASCII to be used in different regions, was to provide a block in that code table where one could substitute other characters, put other characters into the block. So if you were in the United Kingdom, you would have used a version where the pound was placed in that international section. However, the problem was that that same character in the US version was a hash character. So if you encoded something in the United Kingdom and you included a pound sign, then and sent it to someone in the United States, they would see a hash. So to communicate within a region, this international block worked quite well. But to communicate outside regions, this was not a solution whatsoever. One of the major debates when ASCII was designed was the number of bits that should have been included in the code. At that point, when the code was designed, many computers already used 8-bit bytes. But using the argument that we used earlier, that 7 bits would be sufficient, they decided indeed to use a 7-bit code. And the reason for using a 7-bit code is because it is cheaper to transmit 7 bits. You can transmit 7 bits much faster. Your speed in terms of characters per second increases if you use fewer bits per character. So ASCII in the end allows you to represent 128 characters. It includes the capital letters, it includes lowercase letters, it includes the digits, and it includes punctuation, but it also includes a couple of so-called control characters, characters that are intended to be used to control the machine in some way or another. As one example, character 7 has the name bell. And if you send character 7 to an old teletype device, old type of terminal, then it would ring the bell on that terminal. So it means you could output a value, print a value to a device that would not be a visual character that appears, but an action, an audible character. So if the machine wanted to attract your attention, or you as the programmer needed to attract the operator's attention, you could just ring the bell by printing character 7 to it. On a more modern machine, it will issue just a normal beep that you've probably heard on many modern computers. But more interesting for our current purposes is that ASCII included characters that were intended for networking. In networking, you typically have packets of data and you need to delineate those fields. And one of those control characters in ASCII is the start of header. And that as the name indicates, can be used to indicate where the header of your packet starts. There is similarly a start of text, and that indicates where your actual packet, where the body, the payload starts. And various other characters exist that allow you to delineate fields in this manner. There is even an EOT, end of transmission, that you can send to terminate a connection, to break the connection so that no further communication occurs. That is important, or that is useful to have, and many of the older protocols use those characters. Newer protocols tend to ignore them. They have their own means of delineating data, but it is interesting to see how these delineation characters were included in code many years ago. ASCII is a very important code in networks to this day. In fact, it is used in so many network contexts that a decision was made to standardize it. And the ISO, together with another standards body that we don't have to mention right now, got together and they standardized ASCII, and the project that standardized ASCII was 8859. Something needs to be said before we continue with this. Most manufacturers of computers were producing 8-bit machines, as we said earlier. So a lot of them realized that they could use 8-bit character representations. And that means they could add another 128 characters to the set that was defined by ASCII. The problem was that these extended character sets, these additional 128 characters, were not standardized. And different manufacturers produced different extensions. The sort of characters that they included in those extensions include accented characters. So you may, for example, have an A with diaeresis as one example, or you may have an O with an umlaut, or you may have E with a circumflex, or whatever accented character you want, because those characters are not common in US English, but they are common in many other languages in the world. And it made sense to provide some way of representing them, some way of storing them. One of the particular examples, the operating system MS-DOS, which was essentially the same as PC-DOS, and its later successors, Windows, also included extensions. And they included a couple of rather interesting characters in their extended set. A set of brackets, basically brackets like that, and flat lines, and brackets like that, and perhaps upright lines, not perhaps, they did include that, other brackets. And as you can see from that example there, people often use that to draw a nice border around text that they displayed on a screen. The problem was that since that was not standardized, often when you printed that out on a printer, you did not get this nice border that you expected, but you got whatever characters was used by that particular printer in those code positions. So very often it looked like garbage that surrounded your text that you wanted to print out. Now, when ISO standardized these extensions, they realized that multiple extensions existed, and they standardized them with various suffixes. So 8859 suffix 1 is one of the character codes a -2 is another one, and a -3 is another one. We don't have to look at the details of all of those. What this enabled you to do in the first place was to say that I can speak, I as one of the machines, can speak that particular encoding. And when you say I speak that encoding, you tend to write it using hyphens like that. If the computer at the other end can also speak that encoding, then it means you can agree to communicate that encoding. However, that encoding is rather special. Recall that for many values in a protocol, many commands in a protocol, you have to write a specific word. We used the hello example from SMTP earlier. And then somehow that has to be written in a way that all computers can understand. And the encoding, that particular encoding, is the one that is used for these command words. So every computer in the world has to understand that encoding, but it may also understand encodings that are more appropriate for international use. If we take this SMTP example just a little bit further, as you know, when you get to the point where you're going to send the email, you issue the data command. Again, that will be encoded using ISO 8859-1. Now, if the email you want to send happens to be in Chinese, you can enter your Chinese email there. Exactly how that will be done is a topic for a later video, so we don't worry too much about that. But the point is, yet again, that particular encoding of ASCII, or that extension of ASCII, is the one that will be used for these command words. Of course, one of the major challenges of ASCII is that it is restricted to mostly the Latin character set. Yes, it includes an alpha for a little bit of mathematics and so on. But when you begin to think about Chinese, when you think about Korean, when you think about Japanese, all of those languages contain characters that differ significantly from the Latin character set. And there are many of those characters as well. There's no way you can hope to fit them into a character set that only consists of 128 characters. Therefore, we need a different solution. ASCII has its uses, ISO 8859 and family members have their uses, but we have to talk about a way of representing data so that any international character can be represented. We'll do that in a subsequent video.
Music